Need to change video resolution. Okay. Hi, everybody, and thank you for joining us. Greatly appreciate it. Hi, Georgia. You're gonna have to maybe turn off your microphone.
Yep, I will. Just give me 1 second. What's going on here?
Hi, everybody, and thank you for joining us today. It's certainly a pleasure to be here with you today. And today we wanted to go ahead and cover just the subjects about using DRC in your Fusion 360 design. Wanted to go into details on that because there are many times that, yes, trying to get your design ready for a manufacturer sometimes it's not all there. So just wanted to cover a quick tutorial. It's not going to be a really long tutorial. It's going to be a quick tutorial in all the alternatives that exist within DRC and how do you manipulate them and how they can kind of get kind of overridden or overwritten by other parameters that exist. So with not further ado, I'll just let the countdown go for a few 1 more minute. We are hosting webinars every day of the week for Fusion 360. I just wanted to go ahead and share this calendar with you. They're at every day at 2 p.m. Well, almost all of them are. Actually, they have different times. So you have 2 p.m. Eastern, 11 a.m., 2 p.m., and 4 p.m. So just select your favorite subject and go ahead and take a look at those webinars. I've been able to watch several of them, and they certainly are top notch. So let's go ahead and move on over to, let's go live. My name is Edwin Robledo, and I will be directing the presentation today. And with us on the chat, the world-renowned Jorge. Thank you so much for joining me today. And today that we're going to be doing. With no further ado, let's go.
Yeah, you're connected to the right mic. We have one of the guys on the YouTube saying they can't understand you at all. I guess too noisy.
Testing 1 2 3. Testing 1 2 3. Test test test. Is this any better? Can you let me know, George, if they let me know any better?
I can hear you just fine. Let me see if they tell me it sounds better. Just talk a little bit. Can you hear me?
I hear you fine, Jorge. Can you hear me?
Yeah, I hear you fine also.
I switched microphones to see if that was the case.
Audio cutting out, timer not changing. Yeah, your timer hasn't changed. I'm looking on the YouTube. And you're stuck on 238 right now.
Okay, very well. I'm going to go ahead and stop the stream and I'll come right back. Hang on.
Okay. Okay, he says he can hear me okay. So that's good. Okay, how about now? Testing, testing. Ed, are you back in? Did you?
I'm here. I'm with you on Zoom though. I'm not back on the.
Oh, we're not streaming again?
No, we're not streaming at this time.
Okay. Now they're saying they can hear, so whatever came in delayed seems to be okay now.
I think they're on a lag.
Yeah.
It's lagging because I end. Okay. So Ron's saying that he can't hear us now. Then.
Yeah, he is.
Okay. So I think I'll move forward from this point on.
Yeah.
It's just I don't know why my screen isn't catching up, so I'm trying to fix that to see what's going on.
Yeah, go for it. Because right now we just see that 238. Okay.
I'm trying.
Yeah, no worries. Okay.
It should be working about now.
All right. Testing, testing. 1, 2, 3. Testing, testing. Testing, testing. It's going to be annoying, but. Okay. Give me a second.
Okay, gentlemen, thank you for your patience. Very sorry for the delay on starting. I think it's just I was used to using one monitor and I had to switch monitors. And I think that's our feed to give me certain complications. I should be able to get up and running shortly.
So right now we see the YouTube Ed.
Yeah, I guess it's lagging. It will catch up with mine as well now.
Okay, there we go. I see some movement now. Let me go ahead and take it over here. All right, yeah, now it should be okay.
Okay, and it seems that audio is okay as well. Then, so we'll go ahead and take it
Yeah.
off from here. Then, we're very sorry about starting this way. I don't know what happened. I think it was my monitor, maybe that it's the live stream just couldn't handle the resolution, so therefore it was causing a certain amount of lag. Not sure if it has to do with my internet as well. I am on Wi-Fi, so that's just what happens. Now, the topic today is about DRC, and I just wanted to go over this. Um, and it's not going to be a really long presentation. It will be kind of short because we just want to do an overview of the DRC. Now, the DRC stands for Design Rule Checker. In essence, it's the parameters in which you're going to be setting up your design. That way, you can make sure that it's actually manufacturable. That way, it actually works physically. That all the geometry is not overlapping other geometry and so forth. I'm going to be using one of our example files that we had done earlier a few weeks ago, which was one of our introduction designs. It's simple enough in which and complex enough that way I could actually demonstrate all parameters. First thing I want to do is I want to start working from the schematic. Once you're working from a schematic, you're going to be using this icon right here to create the board. Now, once you create the board, all the components of this board editor, of the board layout, are actually going to be appearing on the left-hand side. I therefore actually made some modifications to the board outline and started moving all the components onto the board. Now, before I actually start moving the components in the board, it's always really a good idea to start working with your design rule checks. In other words, that means that I need to continue to start working on to make sure that my board will actually be able to be made. Okay, make sure that it's manufacturable. And what's entitled is that you need to define certain parameters onto the board layout, which will be taking live and affect live on the board. So let's first of all, let's go to the tab here that says DRC. I'll just use my magic arrows here, right here, where it says Rules ERC and DRC. Okay. Now, ERC, when it comes to the board editor, what you see here where it says ERC, that stands for Electrical Rule Checker. On the board layout, that really doesn't do much. The only thing that we use ERC is to check that the board and the schematic have kept consistency. That's what that all means here. So that's the ERC is never really used on the board other than just for consistency purposes. It's a parameter that is basically used on the board layout. DRC is the one we're going to be using on the board layout. So first of all, I'm just going to bring up my DRC panel here. And this is the first screen that comes up on DRC. And this operation should be done before you start making any editing to your board layout. This is the first thing you should do. You shouldn't really be going to the board layout without taking a look at your parameters here first. So first of all, I'm going to take a look at the first tab. It's called Layers. Okay. Now here is where we're going to actually be setting up our layer stack. How many layers is this board going to have? We usually strongly recommend that it's quite common that you only be working with 2 layers, maximum 4 layers. Okay. And how do we switch from 2 layers to 4 layers? Right here in this dialog box, you see down here, there's a parameter here that says 2 layers right there. I'll click on the down arrow, and here I could actually select additional layers that I want to work. Now, layers are always going to be working on pairs. There's no way around it. They always work on pairs. I'm not sure. Jorge, you let me know. Can I send the board house a 3-layer board? Can they actually make it? As far as I know, they can't. You will have to let me know, Jorge. As far as I know, they always works on pairs.
Well, I mean, the main reason is that there's no extra effort in making a 4-layer versus a 3. In fact, it probably would require more effort for them to not use, because when it's built up like a sandwich. You have that middle part, that's the core, and it has copper on both sides. And then if you're going to build up a proper stack up, then you need to keep putting on both sides for everything to be balanced and stable. So for that reason, you won't really ever see numbered layers. But as you can see, if you need 3, you might as well go with 4.
Exactly. Okay. Exactly. Actually, if you send a 3-layer board to a board house, they're gonna maybe say no, or they'll actually make it a 4-layer board anyway. It's just they won't do anything on one of the layers. Period. It's quite possible. It's
yeah, that's what'll happen. And obviously, the good thing is if you got to do anything wacky here, you still have the setup field, and you can manually type in the setup equation. So if there's something weird like having to do multi-layer buried vias or something like that, which is rare, you can make that happen through the setup equation field.
Yeah, I'm going to cover that now right here. That's the setup that we're talking about. But there's two ways you could go about it. You could actually edit this manually, or you could actually take advantage of the Bga Pairs portion of this dialog box as well here. So let's go ahead and change this to a 4-layer board. I'm going to click here and go to 4 layers. I'll select here 4 layers. Okay. Now you notice that now I have the prepeg, which is on the top side here. We have our prepeg, and then we have our core there in the middle, right there. That's our core right there. Okay. Okay. Notice that you have the top layer. It works as a sandwich, as Jorge just mentioned. We work from the top, from the outer layers to the inner layers. So our setup went, you notice that our setup changed. We went from the top layer, and then we have the bottom layer, and then we have layer 15, not layer 3, layer 15, and then we have layer 2, as you could see. Now, there will be times that if your circuit board is so dense or so complex that real estate space is absolutely necessary, and then you could start digging into something called blind and buried vias. Okay, and how do you set blind and buried vias? Okay, you'll notice that we have a little setup right here on the right hand side that says Bga Pairs, right there where it says Bga Pairs, right there. Okay, so here I'll click on the plus sign, and I have a 4-layer setup here, as you could see. I could go from layer 1. It gives me my layer list. I could travel the distance of my vias. Remember, what we're defining here is our vias. So let me explain what a via is. A via is the point of transition that a trace will do to go from one layer, to travel the signal from one layer to another layer. Just want to make sure that everybody here is on the same page. It's just the way it travels from one layer to another way, a trace, okay? So, and I'll show that on the board in a minute before we continue going with DRC. So I'm going to go from layer 1 to layer 2. What this will do is that it will have real estate, it will take up real estate space on layer 1. It will go to layer 2, that trace will travel, but it will not be able to, it won't travel to layer 15, neither layer 16. And this is referred to as a blind via. Okay. As you could see, it automatically comes up here. It says blind via, traveling from layer 1 to layer 2, as you could see here. And then you'll notice that here we get a representation, a graphical representation of the via that's traveling from layer 1 to layer 2, and it doesn't show up on the bottom, as you could see.
Yeah, hence the name blind. And the key advantage is that you're saving space, because wherever you have a hole, that's an area that it makes it more difficult to place any type of components. So in really, really dense layouts, these end up saving real estate on one side of the board. So that's their big claim to fame. They are more expensive to produce, so it's not something you want to use willy-nilly. You really want to make sure that you have no other option but to use a blind via, because they increase the amount of time it takes a board to be manufactured. Remember we were talking about that sandwich process? So basically, if you just have the through hole, the one that goes through the whole board, they can put all the different layers together, and then there's just one drilling operation. But if there's blind vias, what they end up doing is they have to first drill that 1 to 2, then they put the whole sandwich together, and then they drill again 1 through 16. So if you have many configurations like this, it's very easy to see that this can become a very expensive proposition. There are designs that need it. Cell phones are a good example of designs with blind and buried vias. But if you can avoid them, it's just better cost savings for you. So something to keep in mind.
I want to go ahead and expand on that comment that Jorge just did about buried vias. Let's take a look at what buried vias actually do. Hence the name of it, buried. So I'm going to go ahead and click on the plus sign here in the DRC dialog box. I'll click on the plus sign here. And now I'm going to select, I want a via that travel from the internal layer, layer 1, and I want it to travel to layer 15. And I'll click OK. These are vias that are referred to as buried. You'll notice that this via actually travels from one internal layer to another internal layer. Okay. Now this process, yes, as Jorge just mentioned, this process is very expensive now, because now it's a via that you cannot see. Now, why would you do this?
Again, it's to save space. If you really need if your board is that dense and it needs to be that small, and then it may be requiring to have buried vias, as you could see. Now, the process of this is kind of expensive. In addition to that, the process for troubleshooting is quite elaborate when you have buried vias on your design. So they're not really easy to have on the board, okay? Now, notice that as I continue adding buried and blind vias, my formula, my setup actually is continuously changing down here. It's actually being set up for me. If I need to make some manual modifications, I could do it graphically, or I could actually do them right here, as you could see here as well. Okay. Now, let's go ahead and move on to some more parameters in the DRC. I'll go back to the file. Many board houses actually provide a DRC file for you to load. That way you could follow their manufacturing capabilities. In other words, that way you follow their parameters or follow their rules. That way when you send them the boards, since you follow their rules, it's going to be a lot easier for them to make the board. Okay. So you could visit the manufacturer's website, a board house, OSH Park, Royal Circuits, Screaming Circuits, whoever you're going to be using, and you visit their website, and it's quite possible they're going to be identifying their DRC file under Eagle. The Eagle DRC files are compatible with Fusion 360, just to let you know. The extension of that file is going to be DRU. Once you download that DRU file, you're going to go ahead and click here where it says load. And you're going to go ahead and find that DRU file that you've actually downloaded. I think I have a few here, which I could just go ahead and bring up as examples. Give me 1 second. Okay, so here's the DRU file from Euro Circuits out of Germany. And you notice that you can download them. Actually, these actually come with Eagle if you're using Euro Circuits or multi-CB or WeDirect for the PCB services. We already have them included with Fusion, as well as you could download them from their site. So you go here to Euro Circuits, you go to defaults, and here they have setups. You see that they have it for 2 layers, 4 layers, and 6 layers and 8 layer setups. So if you were to download these setup files, I'll just go ahead and select the 4 layer one here. That will go ahead and set up and click open. That will actually now set up your entire parameter under DRC to follow their rules. What are some of the rules that they want you to follow? First of all is the layer stack up. They always want to work between the outer layers to the inner layers. Number 2 is going to be clearances. What clearances do they want you to be following? That way they can make your board easily. That way your board is manufacturable. Now let's go over some of these parameters and their clearances. The clearances tab is basically the distances that are going to be followed, the distances that are going to be allowed between the different assets on your circuit board. The first one you have here is between traces, is between board and board. Let me just move this off to the side a little bit. That way I could compare it to the board. That was my intention on doing this. Okay. So we have wire to wire. In essence, that's the distance that's going to be kept between 2 wires, 2 traces. Next one is wire to pad. That is the distance. And in this case, I was using 7 mils, but usually you may use 6 mils if you have a denser board. You could go lower. You got to be careful with going too low, because then it could create a whole new kind of problems on the board. Also, it may just not be manufacturable. So that's why we always recommend to go to the board house and find out if you could download the DRU file, or take a look. They'll have a page on their website which determines and specifies the parameters that they use for their boards. That way it's easier to make, okay? So that's what I recommend. So here I'm using 7 mils. That's between the 2 traces. Now this is the distance allowed between a surface mount pad and a trace, as well as a through-hole pad and a trace. Okay, so let me go ahead and just click out of here really quick. Okay, and I'll do a quick route here. You notice, I'm going to do this really quick here. I'm doing a quick route here, just a real fast route. That distance that we're seeing is the distance that is being left is going to be allowed between this edge of your trace and this edge of the pad, okay? That's what we're seeing there. So that distance that we see here is that the distance is going to be left there. We could go lower, but we could also go higher. You don't want to go too low. Okay. Now, also, let's talk a little bit about the next one, which is vias. That is a distance that's going to be respected between the vias, okay, between the vias, that's the points of transition, and any trace that does not share the same name. Okay, so let's go ahead and continue to route this one. I will just undo. Design and go to route. I place a via there. You notice that that's the distance now that it's being respected between a trace and the outer edge, the outer ring of this via. It won't go further than that. Okay. 7 mils is actually a really good number to adopt. You could go a little lower, but I actually like using 7 mils as well. Now, I don't want to go ahead and do one at a, I'm going to continue doing all of them, but I don't think I'm going to be going back to the board layout. So here we have from pad to pad, the distance between the pads, distances between pads and vias. Okay, that's surface mount and through hole. So that's basically the distance between our pad edge as well as our via edge right there. Okay.
Yeah. And typically what you're going to see is that board houses will specify all of these to be the same. So usually if you go to a board house and you look at their specs, they'll usually just tell you copper minimum clearance is 7 mil or 6 mil, and that just means that all of these have to be set to the same value. There are rare occasions where the more granular control is useful, but if you're new, just know that 95% of the time you're setting these to be all the same value. And like Ed said, 7 is a good number. Most board houses will do as low as 6 without charging you extra. If you need to go lower than 6, and that's where you'll be paying a bit more for the PCBs.
Excellent. Thank you, George, for that. Now, I wanted to show you that these parameters, these DRC settings are actually live all the time while you design. I'm going to go ahead and select the option manual route. I'm going to go ahead and undo what I've done here. And I'll go ahead and I'm going to do some manual routing. But the manual routing I'm doing, I'm selecting the option that says full control, ignore obstacles. I'm going to take full control of my route just because I want to prove a point. I'm going to go ahead and route this. And as you could see, as soon as I start moving into an area which is a violation, we get those hatch marks as well. Let me go above a red because that way you could see it. Let me switch layers. And as you could see, I get the violations immediately. This is a parameter that you could actually turn off, but we strongly recommend that you do not turn this off. It's really a good idea to always keep this on because in real time, you actually will be able to see what are your DRC errors immediately, okay? I just wanted to bring this up as well. Let's go back to DRC. Okay. Now, we went through clearances. Now, this bottom half here that we have is for items that are of the same signal. If I have two traces next to each other for any reason, and they're both carrying ground, what distance it should actually tell me. Now, these are not going to be really respected by DRC. They're actually going to be allowed because they are actually carrying the same signal. But it's just going to let me know that it will, anything below six mils or below will actually let me know, but if they're sharing the same signals. I don't really mess with this ever, Jorge. Have you ever had to make any modifications here, George, when it comes to same signals for SMDs, pads, and vias?
I've never. The only thing that can sometimes be useful is the ability to set them to 0. Because obviously pads that are of the same signal, if they touch, it's not a short because they're the same signal. So most of the time I don't have to touch this. In a really dense layout, I've heard of users sometimes setting it to 0. That way, if you have pads that are of the same signal, if they touch, not to consider that an error. But that's rare also.
Thank you, Jorge, for that. Yeah, that's about right. Hey, Ron, just to let you know, yeah, this is Ed, and that's Jorge on the other line, just to let you know, and not on the chat as well. I'm glad that you made it. Thank you for being here. And everybody, actually, thank you for joining us. Greatly appreciated. Okay, let's go ahead and move on. Now we're going to work on distances. Um, there's a big difference between clearances and distances, okay? Here we're talking with the inner workings of the circuit board itself. Now here we're going to be working with a totally different program. Now here we're working with copper and dimension layer. And dimension, that's basically the dimension layer, copper. In other words, the dimension layer is where you define your board outline. And let me show this really quick here. This outer layer that you have here, this yellow, that actually creates the separation between the white and the gray, between the white and the gray, the separation line is actually what's called your board outline. And this is a wire that has been drawn on the dimension layer. Fusion 360 identifies that as your board edge. In other words, this is what's going to guide the board house to actually cut your board of this size, of this shape. Okay, this is what's going to actually be guiding whatever parameter they use, their CNC machine or whatever that they use to cut their boards. Okay, so that's what this line is. Now, in essence, what we have is DRC. I'm misusing the command line. I hope you don't mind because I don't want to have to go all the way back over there. In this case, we're actually using 30 mils. In other words, it's going to keep a distance of 30 mils between anything that has to do with copper. It's going to flag. It's going to flag any errors of that are below 30 mil, which is between the anything that has to do with copper and the board edge. I'll show you exactly what happens when I do this. I'm just going to go ahead and move this connector. And as you could see, we get the violation because I am actually below the 30 mils. Now, there'll be instances like this plug. I will actually, most probably, I would actually take it to the edge because it's a side plug, as you could see here. It's a little side plug for this. So I may actually violate it anyway because I actually want that to be sitting on the edge of the board, as you can see here. So I might move it forward this edge, that way it's easier to plug. But so it lets me do it. It's just kind of telling me, look, if you leave it there, you're violating what's your DRC setup for the board edge as well as anything that has to do with copper. So you'll get the same flag if you do any traces below that. Now the drill hole. This is primarily going to refer to the drill hole size for your vias. Drill hole size, we're using 6 mil. So every time that a via is being placed, that hole is going to be of approximately 6 mils. Also, I'm not approximately, it is going to be 6 mils. Every time I use a via, if I'm going to use holes, in other words, non-plated holes, by using the hole command directly on the design, those holes are going to be 6 mils or greater. Okay, remember, this is not setting up the size in stone. It's just letting me know that it needs to be that size or greater. Okay. Now, before I move on, I just want to go back to clearances, George, because this has come up in the past. There'll be instances in which you may pre-set up or have some preferences when it comes to clearances on your board, and that could be overwritten all the way from the schematic. And let's go over to the schematic and see exactly how. And I'm going to be covering this a little bit more a little later. Right now, so I'm going to use the command line and I'm going to type the command class. In class, this actually allows us to set up certain rules for certain designs that are going to be overwritten, that will overwrite whatever parameters we have on DRC. Okay, so let me see if I could just select, I'll select here this one and I'll move it to the side. One moment. Default class. I'll go ahead and create a class. I'll call it power. and I'll take my power and my ground, and I'll set it over here. Now I could go to rules, and here I could say for these two signals, plus V and ground, I could set up a rule that I'm going to use a wire width that is different than the one set up in DRC. So let's say in DRC we had 6 mils. I could go ahead and set these maybe to 12 mils. Yes, because maybe the wire is going to be thicker. Okay. Hit those at 12 mil. That will overwrite. Sorry, let's go back to the board. And I like to show, I could have done this all the way from the board as well. Okay, I could have done this at the board as well. But I actually wanted to do it on the schematic. Yes, because I wanted you to learn that that setup could be done on the schematic. And it's commonly done on the schematic when you have certain preferences on the design. So here I go to DRC. And as you could see, we were here on the distance. We have 30 mils. And we have our hose at 6 mils. But anything that has to do with ground, as well as plus V, is actually going to be using a larger drill hole size. And I could overwrite that over DRC as well. Give me 1 second. I don't know why, but I just got a report that's saying that I've lost consistency between my board and my schematic. So let me go ahead and close the board really quick. Don't save, and yes. Okay. Not sure why I lost consistency. Give me 1 moment. Let me get the ERC report to see if I could just fix it really quick. Oh, it was giving me values, differences. Okay. Apparently I did some sort of an update. So, okay, let me go ahead and move on because it's more about the board layout. Okay, very well. Now let's go ahead and go to continue with DRC. And now let's go to sizes. Okay, this is the second part of classes I want to go to. Now, here what we're going to happen is the following. This sets up what is my minimum width for my traces. That's this one, the first one here. In other words, when I start routing my board, when I use the route command, regardless of the route command, the auto router, any of the quick routes, what trace width it needs to have, at least the smallest trace width it could have before I flag it as an error. In this case, it's using 10 mils, okay? So 10 mils is gonna be our smallest width that we'll be able to use. Now, this can be overwritten as well. Yes, as I showed you a minute ago, in which we were able to overwrite the size of the drill, we could actually do the same thing when it comes to the width that's going to be used on your traces when you're doing some routing. Let me show you how exactly where that's goes. So I'm going to go back to the class. I'm going to go back to classes.
Yeah, kind of a key thing while Ed's writing this out. The key thing to remember with everything in the DRC is that you're setting a minimum. So it's okay to be larger than that, whatever that value is, but what you're really defining is a minimum. So if you need it to be smaller than that, that's where you're going to run into difficulty. So the key is whenever you set in the DRC, that's minimum baseline. From there, everything else can be bigger. Okay, and that's something that comes up with the net classes, because sometimes we see users who try to specify a width that's smaller than what the DRC is specifying, and that doesn't make any sense.
And it keeps on bumping it, and then they
Right.
don't understand why it keeps on bumping it to the minimum. It's like so they need to either set up a net class, as I'm going to show you now, or go into DRC and change that minimum value.
Correct, and you see that in the default net class, which is very important. You notice how it has everything set at 0. Okay, basically the DRC and the net classes are always working together. The larger of the two is going to win. So by setting the default net class to all zeros, this guarantees that by default, the DRC is in control. Okay, then if you have a power net that you need to be wider and you make that width bigger, then in that situation, you'll see that the net class will win because it's larger than the minimum specified by the DRC. So you always have these minimums competing with each other. And that's a key principle to remember when using both the net classes and the DRC.
Thank you, Jorge, for that. Appreciate that. Um, so if I were to route any of these signals that I have here, which I've assigned members to my power, my plus V and my ground, I've set those to 16 mil wire width minimum, as well as using a drill hole size of 12 mil. And I could actually bump up the clearance. So let's say, for example, I wanted these to have a clearance, which by default, if since it says 0, DRC is using 6, I could set this to go ahead and be 12 as well. That way, this entire network will now have that the entire network of power, which is ground and plus V, are going to be using these parameters that we set up. Okay, so let's go ahead and move on to, as you can see, since I set ground, this is kind of funny. Since I set a ground, let's go back to class. I'll show you really quick. I set class for my power. I set the rules of width of 16 mils. This line here, which is actually carrying ground, you'll notice that it has the hatch markings. So it's immediately letting me know, as you can see, it has the hatch markings. It's immediately letting me know that there's a violation here, which in the violation is that I've set the class for ground to 16 mils, while here I'm only using 10 mils, as you can see here. Okay, so that's what's going on. That's why we get that immediately, that error. Okay, let's go back to DRC and keep on looking at some more sizes. Now, minimum drill is the in millimeters is the size for our vias. Minimum drill distance, drill holes, and minimum drill is the size of our drill holes. And this was a distance. Okay, don't confuse it. This is the distance between holes and through hole holes, pad holes, and via holes. And now this is the size of the hole that's actually going to be used. Okay, the size of the hole is going to be used. Okay, now so every time we do a point of transition, that's the hole size it's going to prefer to. It's going to go to that size or larger. Now here in micro vias, I think I'm going to defer to you. I hope you don't mind. Jorge, a micro via only works if you have blind or buried vias set up. Okay, it doesn't work any other way. It won't work any other way. It only works if you have blind and buried vias. And micro vias are vias that are traveling from the center of a surface mounted pad and they go down one layer. Okay, they only go down one layer. Okay, this is commonly used, and correct me if I'm wrong, Jorge, this is commonly used for BGA technology. If you're running on BGAs and you want to do a breakout, usually this is where you're going to be using micro vias. Did I get that about right, George?
Yep. And one key requirement to have the micro vias enabled, besides defining blind vias in your layer setup, is here in the sizes tab, the minimum micro via value, that needs to be smaller than the minimum drill value. Okay, if it's larger than the minimum drill value, then you've disabled micro vias. Okay, so that's the second key requirement. First, you define blind vias one layer deep in your layers tab, and then second, in the sizes tab, you have to make sure that the minimum micro via is smaller than the minimum drill. And this is always going to be the case. Board houses usually use laser machines to do these types of micro vias, and they have to be, they're only worthwhile if they're smaller than the normal drills of the board. So this is in line with how industry works. So just keep that in mind. And I believe actually somewhere in this information, in that description, it actually mentions it, that
it actually gives you a detailed explanation exactly
Yeah.
what's going on right here. It does.
Correct.
Okay. Now, so if you're working with a board and you want to do a BGA breakout, and you're running out of real estate space on the top, this is where this comes to play. And then it will place the via directly in the center of the surface mounted pad, which BGAs are usually round SMD pads. It'll put a dead center of it. It'll go down one layer, and then it will break out from that point on. Okay. And this ratio here is based on the ratio for the blind via, which actually is the ratio, and it takes into consideration the thickness of the board right here, which is this thickness right here. So you got to make sure that that calculation is true. That way this will actually work. Okay. This is how deep it goes right here, the ratio. Okay. Now, let's talk a little bit about the annular ring. Now, in this case, on this board, I don't have any really through-hole parts, if I'm not mistaken. I do not have any through-hole components on this board. So let's go to DRC. Now, here what happens is the following. This shows the amount of plating material. Let me just go ahead and add a component to this design. It is a through-hole part. So let me just do an add command really quick. I just use the single one. I'll put a couple of these. Okay. Okay. Let's explain exactly what we're talking about here. Okay. What we're talking about here is the amount of plating material, or the amount of plating a hole is going to have that makes it conductive. Okay. First of all is right here in the DRC. I hope I accommodate this. That way everybody can see it. Okay. Now, if you notice that we have a minimum and we have a maximum and a percentage rate. What happens is that once I place a via on my board, a pad on my board, a through-hole pad, it actually has a drill hole size, which is brought up from the library. This is the size of the hole that was determined on the board when I'm creating the component in the library. Now, the amount of plating material is this donut effect that it creates here. This is the amount of plating that is for the board. In other words, when a trace attaches to this,
By the way, guys, this is the one that tends to cause everybody trouble.
Yes, so that's why I'm getting all specific with it, because it is the one that can cause certain confusion, and I'm gonna explain why in a minute. That's why I just want to run this trace really quick here. Okay, so what happens is that that parameter. Oh, let me bring it back up. I'll be honest with you, Jorge. My whole inspiration for this webinar was this. That was my whole inspiration here. Now, let's go to annular ring. What happens is the following. So the annular ring controls the size of this plating material that you have here. Okay. So it's the size that's going to be on the top layer, and it could be different on the bottom layer, and it could be different on the internal layers. Now, this column for minimums is how big it's going to, what's the smallest it will be, how much plating material, what is the minimum? The maximum refers to what's the largest size it will go. Okay, what's the largest size? And the percentage actually defines, based on the hole, the percentage it's going to be here. And I think Jorge has a better explanation to me when it comes to the percentage. Could you tell us a little bit about that, Jorge?
Yes. So here's how this works. So what Eagle will do is, sorry, not Eagle, Fusion Electronics. Old habits die hard. What you'll do is it will look at the drill value. The drill value is immutable. That's non-negotiable. Whatever you set as a drill, as the actual hole, that will not change. Now, the overall diameter, the thickness of that ring, that will change, and that is negotiable. And here's how the calculation works. Basically, whatever the percentage you've defined here is, it will take the drill value, multiply it by that percentage, and it will achieve a restring value, an annular ring value, basically a thickness. It will compare it to the minimum and the maximum. If it's less than the minimum, it'll be bumped up to the minimum. If it's more than the maximum, it'll be brought down to the maximum. Okay? The final diameter is that annular ring value times 2, because obviously you have a thickness on both sides, plus the drill. Okay? So as an easy example, let's say we have a 10 mil hole. Okay, 25% of 10 gives you 2.5. 2.5 is less than 10, so now we're going to use, right? 2.5 is less than the minimum of 10. So now we're going to use that minimum value as our annular ring value. So the finished diameter is going to be 2 times 10, which is 20, plus the drill value, which is 10. So in total, the finished diameter is 30. Now all of this is pretty straightforward. Where it gets confusing is when users in the library specify a diameter.
Correct.
You know, in the library, let's say I have the same 10 mil drill, right? But I've specified the diameter of the pad should be 20 mils. When I bring it into my design, the initial reaction tends to be one of confusion because the pad has now swollen to a diameter of 30 mils. And if you don't know that this feature is in play, you start freaking out because it looks like something has gone horribly wrong. But what happens is annular ring settings are always in play. They can't be overridden. So what happens is Eagle will look at the diameter you've specified in the library, compare it to what the annular ring calculation gives. The bigger of the two will win. Okay? So if you run into that situation where you bring in a component and the pads have swollen, they've gotten larger, the solution is to go into the annular ring settings and modify them just enough so that what you've defined in the library wins. And the reason I said just enough is because the annular ring settings are global. They affect the entire board. So you only want to adjust them as much as necessary to get the result you need.
Correct. So you broke out there just a minute ago, Jorge, just to let you know. It was just for a few seconds, but it was kind of key. What Jorge was saying at that moment was that it when you bring it into the board, you'll notice that your pads are swollen compared to the value that you had set for your pads diameter on the actual library. What happens is that um, Fusion 360 will use the value that wins, whatever is larger. So if the calculated value by the annular ring is larger compared to the value in the library, that one was going to be used, the calculated one. Now, if the value of the annular ring, if the value in the library is larger than the calculated value in the annular ring, and then it will use the one in the library. Okay, so I just wanted to bring that up because you just got cut off really quick. Now, if you want to use the ones in the library, which we already heard, is that you could actually modify these values, make them smaller. That way, the value used in the library is actually used here. You change these values, make them smaller, and make change the percentage to a smaller value, change your minimum to a different value. That way, now the value you have in the library wins or is larger. That way it wins. That way it actually takes effect. Now, Jorge, and I'll bring up one more other observation that I've noticed on some boards in which users actually have set up they've set up the percentage to like 1%, and they set the minimum and the maximum to the same value. Therefore, it's using that same ratio for all of the pads on the board. Not sure if that's a good idea, but I've seen some small boards that they actually just go ahead and do that. That way
Yeah.
they're in better control.
Yeah, it depends on the board house because if the board house specifies a minimum annular ring, then some users will do that. They'll just set everything on the board to that minimum.
Mhm.
It's not always that easy because if for some board houses it is kind of a proportional type of relationship. So the bigger the drill is, the less annular ring it needs. So that can pop up. But usually, if that situation crops up, that's not a bad way to approach it. It all depends on what your manufacturer can do.
Exactly. Now, and remember, the for vias, you're in control of the plating on the top, on the bottom, and for the internal layers. So you have those three parameters that you could actually modify. Now for vias, we only have top or bottom. The precedence is exactly the same way. Same way that we just explained the pads, same happens for vias. As you remember, for sizes, we actually define the size, the drill hole size of our vias, as you could see there. That's what we set up. We set that up. Therefore, the annular ring is now calculated by, it calculates our vias for the top or for the bottom. Now there's no inner layer here, so it's this whatever size it uses is not negotiable. It's just the right size that it uses. So you only can control the top as well as the bottom. And as we said earlier on our micro VS, if you're going to be using micro VS, it's just the size that is going to be used right there in this parameter that you see right here. Remember that we were talking about micro VS right here? So that's just how big the plating is going to be for our micro VS. Okay. So any questions, Jorge, so far on this area? And I'll be really honest with you. As I said earlier, this is really what I wanted to cover in today's webinar because of that confusion of bringing in components to your board and the actual pad size. It looks different. Now,
A few questions have popped up, but I've been able to handle them so far, so there's nothing outstanding right now, Ed.
okay, cool. Thank you, Jorge. Appreciate that. Oh, and hi to everybody. Thank you for joining us today. Okay. Now, I was looking at the chat. Just want to say hi to everybody that's joining us today. We got a full room today going on. Now, let's talk a little bit about shapes. This is a method by which you could actually kind of overwrite settings that you have on the actual board, on the library, I should say. So I don't really like using this that much. I prefer using it on the library because it's sustainable. But what this is that in this case, let's say if I have through hole pads on my design, as you can see here, I could actually modify the roundness factor that the surface mount components have. Again, I don't really like doing this here on the board, but on the board I prefer to do it in the library. But you could actually modify that roundness. That's the, as you can see here, that sharp corner that we have here. If you change that value there, it actually takes effect on all of my SMDs. Now, it take effects on all my parts. It doesn't take effect on particular parts. You cannot control it by component. It's controlled by the entire board. Same thing goes here. And this one I've actually used in this one here. So as you create components in the library editor, you identify them by pad 1, 2, 3, 4, and so forth. You can actually change the shape of that pad on the top, on the top or one of the layers, top or bottom. That way, that shape is actually as in the library. That's this one right here. The pad number 1 first. That way, you could easily identify which one is going to be pad 1 or which one is going to be pad 1. Okay, so I could actually change it here to a square pad if you needed to. That way it could identify, especially on ICs. Now, top and bottom pads is I could change them all to square or round or just keep it as what is in the library. These are parameters I don't really like messing with. And if you need to modify the elongation of a Y long or X long pad, these are where you actually would change those parameters. So you actually shrink it is basically what you do. So here it actually shrinks it, and then out here you actually shift it is what you do. Again, I prefer to recommend doing this in the library than here on the board layout. Okay. Okay, very well. Now, when it comes to thermal isolation is the distance that is going to be left for components that actually connect to a polygon. So let's go ahead and do this really quick. Okay, very well. As you see here is the isolation. The thermal isolation is the distance that is gonna be leaving to connect to the actual polygon that you have right here, as you can see here. And then also, I have. Let me see if I have any ground vias here. No, I don't have any ground vias going on here. But if I did have any ground vias in here, I would actually set up. If I want thermal connections to my vias, I would actually select this option. Usually when it comes to Polygon for vias, since you're not soldering anything to a via, it's not necessary to have thermals for it. So that's why we have this set up as deselected, because it's just not really necessary. But for pads, of course, the reason we have thermals is that way heat could build up. That way you could solder the part. If the pad was swallowed by the polygon, it would be really difficult to actually solder to it, because heat would just continue dissipating too fast and never able to build up. And here's where you actually have certain control of this thermal distance. So let's say I change this to like 40, so that way you can see what happens. Okay, and then we run rat's nest. As you can see, it's so big that it's not able to generate it. So let's go back to DRC and we go to supply, and let's change this to like 5 mils. You're going to see how much tighter it gets. Apply, and then I'll go back to the board and run rat's nest. Remember, you use the rat's nest command for polygons to calculate, and every time I change a parameter, I need to force it to recalculate. Okay, so you notice that it got a lot closer here. See, so you notice that what we're working is with this distance right there between the edge of the pad and the polygon. That's what we're working with. That's what that's controlling. Okay. So that's what we're controlling. So this parameter is actually controlling that distance, as you see right there. That distance right there. Okay. By default, we have it set to 10 mil. And usually that's a value that is more than effective. Now, mask. This is another one that sometimes gets a little confusing because how different it works with surface mounted pads as well as with through hole pads. So let me turn on the mask layer. That way you can see. The mask layer is, if you've ever looked, I'm sure all of you have, looked at circuit boards, the majority of them look kind of green. Let me show you more or less what they look like. I'm sure you all have seen this as well. Let me change this color that way. I change my solder mask color. I'll change it to a green color. Oh wait, it's a little bit more obvious. Okay. Flip it around. Let's take a look at the bottom. I think there's more traces on the bottom. Okay, as you could see. So here, I'm going to use this one as an example. This green material is that film, is that solder mask, is the film that they put over the board to protect all your traces. Now, your components are actually exposed. They're landings, not the components, the landings. In other words, the soldering points are actually exposed. That way you could solder your point. This is the exposed copper, what we refer to as landings. As you could see, we always have like a little distance going on there. Okay, that's the distance that we're getting from here. Let me zoom in on this a little bit more. That way you could see it. That's the distance that we're getting from here to the actual edge of the landing. That's what that's controlling. So let me go back to DRC. Mask. Okay. So the distance that it's leaving, that way we could solder the points. On the stop layer, it's actually going to be around 4 mil from the distance of the actual pad. So it's actually a calculated value, very similar to the way that we did the annular ring. Is that about right, Jorge?
Correct. So here it's the same kind of idea as the annular ring setup, but what you'll notice is by default, the expansion is always steady for all the components. So by default, we give everything a 4 mil a 4 mil expansion on the stop mask. So in other words, around the pad, there's an extra 0.004 of an inch of space where the stop mask isn't there. That way we can make sure that we can solder properly. Now you can obviously control that to whatever the board house needs. So you can see that's just a little bit extra margin to make sure that there's no solder mask on the pad itself. And 4 mils is a good number. Very rarely do you have to change it. So in that regard, you know, that if you're not sure, if your board house doesn't specify anything, you can just keep going with it like that. Now the cream, which Ed has here, kind of works a little backwards compared to the stop. Instead of expanding away from the pad, it expands into it. So it's almost like a negative. It cuts into the pad. And when Ed selects that parameter, you'll see that the picture changes to indicate how cream is treated.
So let me, so before I move on to cream, so this hatch marking, as you see here, is the clearance, the opening that is going to be left for this pad. It's a negative image, as he mentioned that way. But let me go ahead, and for the cream, it's totally different. It's a negative port. It's a negative value. So let me just go ahead and enable that layer. That way you can see how it works here on the surface mounted pad. So this is an SMD pad. I'm going to eliminate the T-stop layer and turn on the cream layer. Okay. Did I do it right? Let me turn off the T-stop and turn on the T-cream.
Nope,
Okay.
you did. You got to say okay,
Yeah.
remember?
Yeah, I did. Okay. Now, you'll notice that now, instead of being an oversize, it's actually the same size of the surface mounted pad. And that's intentional. That's it could be controlled, but it's intentional. So we go back here to mask, and you notice that we have all the values for the cream to 0. Therefore, it's actually going to create the opening for the surface mounted pad that is right up to the edge of the surface mounted pad. And this is desired behavior. We want it that big or smaller. So if I change the percentage here, let's say I change this to 5%. Let me see if it takes effect.
Well, it won't, because the minimum and the max are set to the same. When the minimum and the max are the same value, percentage has no bearing. Okay. Because there's no wiggle room for the number to vary.
So I set the maximum and the minimum 10 mil, and I set the percentage to 5%. So therefore, you'll see that the only portion that is going to be exposed now is this portion here where you see the hatch marks right there. As you could see, let me get rid of these. As you can see, now it's only going to be exposing this amount of copper. Everything else is going to be underneath the solder mask, as you could see. Now, I'll put these back to 0 as they go. Apply. Now, an interesting of the cream layer is that the cream layer is often used to create your stencil. Actually, that's where I've been using it the most. Is I will submit the Gerber file with that layer enabled, because that's the layer that's going to be used to create my stencil. That way I can actually now pour solder paste on it. So let's take a look at what that layer looks when I generate the copper layer. So I'll turn this off. I'll turn off all layers. Only turn on the cream layer. T-cream. That's the T-cream. That's the top side. So I'll make a stencil with only this. I'll make a Gerber file only with this layer, and I'll send it to like OSH Stencil or any other board house that makes stencils, and I will get back a stencil that just has the pads that are actually exposed. So if I turn on the top layer, you notice it's the exact same size. I don't have one here at my house. If we were in the office, we have plenty of stencils there. I would be able to show you what it looks like. It could be out of plastic, it could be out of metal, sheets of metal as well. And this process is usually used if you have a reflow oven. That way you put it over your board, you just cover it with solder paste, put your ports on the board, and then put that in the oven. And usually it takes around 7 to 8 minutes to get your boards baked, and all your components are actually soldered to the board. So that's what that value actually controls. Okay. Did I get that right, George?
Yep.
Okay, very well. Now, last but not least, the limit. The limit is a value that is set for, let me see if I remember this correctly. So there'll be instances that you want vias to be exposed and some vias to not be exposed. Okay, so on the solder mask layer, so this limit value is that threshold. So if I was to set this value to, let's say, for 16 mil drill hole, 60 mil, that means that every hole that has 16 mils or greater will be exposed, and anything that's 16 mils or lower will be tinted, will be covered with the solder mask. That's what this limit does. It kind of lets you control which vias you want them tinted and which vias you want exposed. That's what this is. Um, I've only seen a few instances that this is actually used because somebody's going to use once they expose a via, because maybe they want to use it for ground and they're going to solder a pin there, or they're going to, they want to expose because there's going to be a screw there and it's going to be going to ground. So that's the only instances I've actually seen in which they actually want their vias being exposed, and they will use the limit values here as well. Did I get that right, Jorge?
Correct. Basically, in very, very dense layouts where you still have lots of vias, there's a lot of potential for shorting, especially in a manufacturing context, where if you have solder paste near these vias and it touches, then it'll draw solder away. So in those situations, tenting, as this process is called, where vias are are covered so that way you can't solder to them. Well, that prevents the shorts, makes the board more reliable. So that's where this value comes into play. It is global, and usually it's not very granular. So what most users that have that requirement will do is that they'll make sure that the vias that they want to make sure get covered are smaller than everything else, have a unique size to them, or maybe a unique range of sizes, and everything else is bigger than that. That way it's easy to define a limit value. Ed, I think you're muted.
Yep, sorry about that. Yep,
Oh,
I'm
there we
here.
go.
Yeah, so just want to cover the very last tab, which is the miscellaneous. In essence, here we're going to select what exactly the DRC is going to check for me. What is it going to be checking? Um, there are many parameters or many parts of the circuit board that it's not really all that necessary to check. So therefore, but they can be important to a particular design. So you may have to select them. So let me just so here it checks the font. Of course, if you're going to be using on a circuit board, remember that when you're going to output the Gerber files, it's only going to be using vector fonts. Therefore, if you use any of the other two fonts that we have on the design, you'll get kind of an error because what you see on the circuit board is not what you're going to get. Okay. Angle, this is kind of a legacy parameter. Back in the day, it was just because what users preferred actually, or what could be easily manufactured, which was any angle other than 90 and 45s would actually be checked, but that's not really the case any longer. um, it does actually let you know if you draw any shapes on the restrict layer, any restrictions on the restrict layer. It actually kind of lets you know if you have two items, two assets on the circuit board which are drawn on the restrict layer. It will actually let you know that there's a DRC violation there, and it's always a good idea to keep that one turned on. Um, Now for the solder for check stop values for stop and value layers, these are not really that necessary, to be honest with you. Um, it's just taking a look at the values that are being used for the stop layers as well as the value layers. Value layers is not commonly done on the circuit board. Usually it's omitted, therefore we have it omitted here as well. So it doesn't really check for that as well. Um, Check names and on the check name layer. So that's the names of your components. It actually takes a look at what's going on, if it has it. And if I think Jorge, am I correct that if it checks to see if it's exposed is what this one does?
Which one?
Check name layers.
I don't remember exactly what that one does. That one, I think, just checks to see if they're on the board,
Okay, very well. Okay,
if they have
very well.
content in them.
It's a little confusing me. I had checked this earlier and then now I just got confused. Check wire stubs. Could you tell us a little bit about that one, Jorge? Because I
Yeah,
remember when they installed this one.
yeah. So basically, that one checks for traces that go nowhere. So sometimes you can have, if you're not careful while routing, you can have like these little segments that remain but aren't ending at a connection point. They're just kind of floating in space a little bit, and that's what that check looks for. Sometimes it can be a little bit of a red herring or of kind of a false positive situation, because sometimes it'll find a little segment within the pad itself. And obviously, if you continued production with that, it wouldn't change it. It wouldn't create an issue. But still, you want to maintain netlist integrity, so it is good to still find them.
Exactly. And the last one, but not least, is called check for the width of the polygons. Remember, polygons is a whole bunch of wires next to each other that raster to create the effect of a solid, as you see here. Now, polygons can have a wire width on them. And let me see if I could actually select the wire width. Let me just unpour this one. And I'll just go here. And polygons actually have a wire width, as you see here, which is using a 6 mils wire width. I'll just make a side note here. Always use a value of like 6 mils or greater. Some users, to have a better resolution, will set this really small to like 0. In addition to the thermal connections being way too small that they won't really work, in addition to that, it will create an immense amount of data when you generate your Gerber file. So you want to use values of 6 mils or actually greater at that point.
Yeah, basically 2 rules. Don't use 0 ever. And then the second one is use the biggest width that gives you an acceptable resolution. You know, you have that trade-off, but you can manage it. The larger the width, the less resolution, but also the faster the CAM processor will run and the less data you'll generate. So you just got to find the sweet spot. As long as it's not 0, you're probably okay.
Excellent. Thank you, George. Now, let's go back to DRC, manufacturing, and go back to, back to DRC. Now, last but not least, we're on the miscellaneous tab right here. We're going to talk a little bit about differential pairs. Now, the differential pairs is the maximum length of a differential pair, as well as the gap factor on differential pairs. I don't have a differential pair defined here, but in essence is the way that you control the length of a trace on the board. And what this does is that it controls the amount of meandering that's going to be used on the board. Could you tell us a little bit about that, Jorge?
Yeah, so the first attribute is basically the tolerance. When you use differential pairs, you'll notice that if there's a big discrepancy between them, the color of the value of the length value will be red. Once they're within the tolerance, they'll both go green. So 10 millimeters here is defining that threshold of when it will go green, when it will let you know that they're close enough, they're good enough. 10 millimeters is very large. I think USB 2.0 or 3.0 requires at a maximum 2 millimeters as the difference between two traces, the differential pairs on the USB bus. But 10 basically is treating it almost like a don't care. In the case of the gap factor, that one is important. What it will do is it basically determines the distance between the coils, between the loops. The smaller this value, the tighter the coils can be. This default value is kind of large. I find that it doesn't tend to be very helpful, especially on a dense setting, on a dense layout. So what I will typically do if I have a lot of differential pairs to deal with is that I will set that gap factor to something like 1. So I'll take it from 2.5 to 1, and that allows me to have tighter coils. See, so right there, you can see that it's giving Ed, once it's 10 millimeters away from that 2000 mil value, it'll go green.
There it is. I changed the value to 1900 that way.
So that's what that's controlling. It's basically how close are you to that target for it to be acceptable.
Thank you, Jorge, for that. Appreciate that.
Mm-hmm.
Okay. So now we talked about differential pairs and the gaps, but let's talk a little bit of what is this is for length matching. Okay. It's very commonly used for USBs. Okay. Length matching. I plan to do a small tutorial how to actually use length matching. In essence, you need to name the signals with a particular characteristic. That way you have differential pairs. Then you could follow with a length match route and you could complete it with meandering. That way you have the exact same length. And this is usually done with DRCs. There's some other aspects of the board that actually require them because it cancels it out. So we'll work on that as well. Okay. Well, this covers everything that I wanted to cover today about DRCs. We went into details on it. Now you should be able to load your DRCs and look through the DRC parameter each tab at a time and have a good idea exactly what they define and how they affect on the board. Okay. Thank you very much, Jorge. I greatly appreciate it. Make sure that you visit us on the Fusion 360 Electronics forum page if you have any questions, and we'll go ahead and address them at that point on. Thank you so much, Jorge. Amazing job by participating with us as well as running the chat. I greatly appreciate it. Everybody on the forum that joined, I'm sorry, everybody on the chat that joined us today. Thank you so much for coming. Many of you are actually been here before. Thank you for returning. Everybody have a great day and thank you. Thank you, George.
Bye, everyone. Thank you for joining us. Thank you, everyone. We're still live, Ed.
Okay, we're done.
Yeah, we're still streaming. You got to kill it in YouTube.
I did.
Okay.
It has a little gap there.
Okay. Good job, Ed.
Oh,
That was a
okay.
long one.
I thought it was going to be a lot smaller, to be honest with you.
Yeah. It's all right.
Hey, George, by